Hi, everybody. I'm George Omdahl. I am a senior analyst here at PAI, and I am also part of the HERO development team. I've been working on Inception, and so I'm going to be walking you through our presentation today. So, with that said, let's jump in. So, let's start by. Could I just remind everyone to please mute their lines just to make sure that there's not any noise coming through? Thank you. So to talk a little bit about the development history of heRo3, we've been working on it for about 3 years now, and it's undergone many different evolutions over that time. But in its most recent form, in 2017, we got Merck, Amgen, and Novartis to commit $375,000 in unrestricted funding for the final phase of heRo3 development. I would note that those development partners have no interest in control over heRo3, so it's still owned entirely by PAI. And heRo3 is going to be available for deployment and use by anyone who would like to participate, not just those development partners. Pilot testing of heRo3 began in November 2017 and is currently ongoing. And 200 plus analysts and modelers have been involved in that beta testing. We expect the official launch of heRo3 to occur in Q2 of this year. So heRo3 is our web-based platform for building cost-effectiveness models as interactive web applications, either in the cloud or behind the corporate firewall. And the calculations for these models are performed using open source health economic modeling packages written in R. And so the main one is called heRo3, which is an offshoot of a package called heMod. And so all the code behind this is open source. Now, heRo3 currently supports development and deployment of Markov, cohort, and partition survival models. However, we expect that to grow into things like microsimulation models, dice models, and similar models as the platform continues to grow and advance. So this is, of course, a new paradigm compared with the way that health economic models have been developed previously. I mean, typically they're developed in Excel. So why do we need this new paradigm? So there are a number of problems with the existing paradigm. For one, most of these models are developed on a bespoke basis, and so there's not a lot of efficiencies currently to be had in their development. We reinvent the wheel every time, pretty much with every model, and that's not efficient. Because we're reinventing the wheel every time, it's resulting in a lot of errors that need to be checked every single time. So every model is its own piece of software that requires its own sort of complete front-to-back check. It also results in a lot of training costs because each model is its own piece of software. Each model requires its own user guide and its own sort of period of time where modelers become comfortable with that model. When a new model is passed from the people who develop it to a local group that needs to adapt that model, they need to relearn that model. They need to sort of treat it as a new piece of software that they need to learn, and that takes time, and that time costs a lot of money. And so really, how does heRo3 improve upon those current weaknesses in the paradigm? So one thing is we believe it provides enhanced transparency and robustness. Because all of the calculations in heRo3 are performed using open source code, it's possible to check all of the code that's behind all of this, and this is the code that's used for every model that's built in heRo3, and so all of it can be checked once and made sure that it works properly. All of the code includes tests that are run every time a new version is released to ensure that that code continues to function properly. And so this creates potentially a common code base for a really wide range of models where they can all point to the fact that this code base is available and validated and transparent. And we believe that's a large advantage. Another advantage here is the programming efficiencies and the resulting cost savings that this platform is going to provide. So heRo3 makes it a lot faster to build models. It makes it relatively complicated model structures in Excel pretty easy to do on this platform. There are things that in Excel will take days to do that can be done in minutes or hours on this platform. And we believe that that's going to result in some pretty extraordinary savings. Additionally, this is a structured framework for model building. So one problem with Excel is that it totally lacks structure. Every modeler can build the same model in a totally different way and lay it out in a different way. And that results in a lot of sort of challenges when it comes to understanding a model and ensuring that best practices are followed. Because we use a structured process for building models, we ensure greater consistency between models that are produced, and we guide people towards using best practices. And so it's a lot easier to ensure the consistency and quality of models produced using heRo3 as compared with the existing paradigm. Another advantage of heRo3 is that it provides engaging graphical interfaces and displays. Excel is not really the best platform for user interfaces. It also is somewhat limited when it comes to the visualizations that are provided. With a model that's built in using heRo3, you will get a comprehensive set of visualizations out of the box, which we have really crafted to really show the important aspects of a model, important results, and to make it really easy to understand what's going on in your model. So additionally, there's improved version control and lifecycle management with models built using heRo3. Once the launch is completed and we're ready to go, models are going to be stored centrally on the server. And what that means is that if you've got a model and you at some point discover that you've made an error in that model and you need to update it, once you save that model and make it available to people, they're going to be able to get the updated version of that model. And so when they go to the URL associated with that model, they're going to get the newest version of it. Whereas, yes, and of course all of this is behind a firewall, and so people will not be able to get access to it who aren't supposed to get access to it. But pushing out a new model in heRo3 is a much better process than in Excel, where you may not even know who has access to the model in Excel because it gets emailed out. Whereas this platform, once you update the model, everyone gets access to that new version of it. So another aspect of it is that we believe that this platform provides a deeper understanding for how models work. The platform is really structured around making it easy to get instant feedback for the changes that you are making. And so regardless of what parameters you change, you can take a look at the impact of any parameter on any output and see the impact of that parameter in real time on that output. And all of the charts are built in with sort of nice transitional animations, which will make it very clear what the relationships and value drivers are between the different parts of your model. So a little bit about the platform itself. So we think of heRo3 as a secure platform and interface, user interface, for running open source modeling packages in R. And so the process is that through our user interface, you create a model and view the results of that model. Now, while that's happening on the server in the back end of this application, the calculations behind your model are being performed in R. And so your front end, your web browser is sending the contents of the model to the server, which does the calculation, and that sends back the results for display on your local device. And so with this system, heRo3 lets you build models that are effectively written in R, but it doesn't require you to have any real programming experience in R. Really the level at which you need to engage in R in this platform is just at the level of building simple formulas which are more or less the equivalent of Excel formulas. heRo3 is also going to be mobile friendly, and that's going to allow you to deploy your cost effectiveness models on mobile devices in the near future. So a little bit more about the modeling packages behind heRo3. And so the way it works is you define your model as a series of tables which make up the structure of the model. And the calculations that are necessary within those models, for example, the calculations of the transition matrix, those are defined using short R expressions, which are similar to Excel formulas. And within those within those short R expressions, we have a set of special keywords and functions which can be used to vastly simplify the process of defining certain aspects of your model. For example, the creation of tunnel states within a Markov model. And we'll see some examples of how those keywords and functions can make complicated things simple later in this presentation. However, I'd note that a full list of those keywords and functions is found at the end of this presentation, and we'll circulate it afterwards so you'll be able to reference it. With that, I'd like to get into the steps, the actual steps involved in building a model in heRo3. And so we have an 8-step process that you can go through to build a model. So the first step is decision. We're going to skip over that. That's not fully implemented at the moment, but that's essentially a question of what kind of comparison, what kind of decision is being made between different strategies. Number 2 is setting. So this is things like the country, the time frame, the cycle length, discount rates. Step 3 is groups, and this is where we define the population of patients being considered. So if we have a homogeneous population, nothing needs to be defined. We just have a single group of patients who are all the same. If we're modeling a heterogeneous population, then we can define different groups of patients who differ on specific attributes, and then those attributes can be used in the calculations of cost and outcomes. Next we have states. So there we define the different health states in the model. 5 is strategies, so the different strategies that are being compared within the model. 6 is transitions, so that's where we define the probabilities of moving from between health states. For a Markov cohort model, that involves defining a transition matrix. For a partition survival model, it involves defining distributions of PFS and OS. Step 7 is values, and this is where we define individual line items for cost and outcomes that are associated with either state residency or with transitions between states. So, for example, this is where we would define medication costs, or this is where we would define pre-progression life years in a partition survival model. So with different line items that are in outcomes and costs are defined in the values page. And then finally, the 8th step is summary, and this is where we aggregate those outcomes and costs into sort of overall measures. So this would be things like defining qualities as the sum of pre-progression qualities and post-progression qualities in a partition survival model, or defining our healthcare system costs as the sum of medication cost, other care costs, terminal care costs, etc. And essentially every summary is either a numerator or a denominator, a potential numerator or denominator in ACE ratio, as well as an outcome that can be looked at on its own. So, soon we're going to jump into a specific example, walking through those 8 steps and sort of how they shake out for a specific example. But first, just a few words about the formalism involved in heRo3. So we believe that formalism is central to why heRo3 works. Formalism, of course, is completely lacking in Excel. When you start a new model of Excel, you start with a blank workbook. You're given no structure whatsoever to work with. Whereas in heRo3, because it walks you through these steps, it creates a consistent framework for how models get defined. And we believe that, as we mentioned previously, that's going to substantially increase the consistency and the quality of models and foster best practices. So, for our first example, we're going to build a simple Markov cohort model. It's going to involve 2 strategies, a standard of care / natural history strategy, and a new drug. We're going to have 3 health states, just to keep it simple for this first example. We're going to have well, sick, and dead. And so patients can go from, well to sick, well to dead. They can go from sick to dead. And, of course, they can stay in their current states. Our cycle length is going to be 1 year, and we're going to run it for a total of 20 cycles. And we're going to produce outputs for costs, life years, qualities, as well as the ICER based off of dollars per life year, dollars per quality. And so with that, I'm going to jump into a demo. And so over here, I have this model opened up in the heRo platform. At the top, you will note that there is a sort of a subway diagram here, which represents the 8 different steps that we go through when building the model. And so right now we're on step 1, decision. And as I mentioned, that's not currently implemented, so we're going to skip over that into the second step, settings. And here you can see we've set the country to the United States. We've set discount rates for costs and outcomes of 3%. We've set a cycle length of 1 year and a time frame of 20 years, as mentioned previously. So next we're going to go to the groups page, and here we haven't defined any groups because this is a homogeneous model. It is simply one group of patients, so we don't need to differentiate them. On the states page, we've defined states for well, sick, and dead. And you can see here we've defined initial probabilities for being in those states. So everybody starts in the well state, so the probability of being in that well state initially is 1. For strategies, we've got our natural history strategy and our new treatment strategy. They're both checked here, so that means that they're both going to be included in results. If you have 3 or more strategies, then you can check or uncheck ones that you don't want to be included. So it's easy to include a bunch of strategies in a model and then move them out of the way as needed. Now, the next step is transitions. And on transitions, now is where we're really going to start to get into the calculations behind the model. So previously, we're defining structure, but now we're really getting into the calculations. And so this table that we have on this transition page defines the transition matrices for both the new strategy as well as the natural history strategy. And the way they're defined is through a long-form table with columns for strategy, from state, to state, and then formula, which is an R expression. And so the strategy column, or just more generally, each one of these rows represents an entry in one or more transition matrices, where the from state represents, which row it's in, and the to state represents which column it's in. So we're just defining different cells in that transition matrix. Rows that are not sort of included in here are just assumed to be 0. So in this table, we're only including the transitions which are possible. For example, we don't have a transition here from the dead state to the sick state because, of course, that wouldn't be possible. Now, you'll note that some of these transitions specifically reference the natural history or the new strategy. That's because that the formula for those transitions differs by strategy. Whereas other transitions, for example, the probability of going from the well state to the dead state, does not differ by strategy. It's just set as all. And so all strategies, both natural history and the new strategy, will use this formula for calculating the probability of dying from the well state. And so like this, we define our transition matrices for the 2 strategies. But just a word on the formula here. So we're referencing some variables that we've defined elsewhere in this model. So let me show you where that's going on. So this formula here, for example, for the probability of going from well to sick, there's a formula here that references this variable, P6NAS, the probability of getting sick for the natural history strategy. So that is defined in the variables page, which you can find on this left-hand sidebar. So right now we're in this pencil icon right here, which we call the model editor. Below that, there's the variables page, where we define the different input variables and intermediate calculations in the model. So we're going to jump over there. And over here, you'll see that we've got a bunch of variables defined. So this is just an inventory of our variables. Oftentimes in Excel models, you have a similar worksheet where you do an inventory of these different variables, and that's what we have here. And you can find this variable P6NAT right here. And you can see we've defined the value of that as 0.5. And so there's a 50% chance of undergoing that probability each cycle. And there are various other variables here that are defined, some different transition probabilities that are being used in that matrix, and we're just referencing those on the transitions page. Now on this variables page, you can define input variables, essentially just by in the formula typing in some kind of constant. But you can also do intermediate calculations. So just as an example here, we have a utility value for the 6th state right here. And in the formula column for this, we're defining a calculation which references a couple other variables that we define. So for example, we're defining the utility value for the 6th state by taking the utility value for the well state and subtracting a disutility for being sick. And so on this variables page, we can do any kind of sort of defining input variables or defining intermediate calculations, and then these variables can be referenced on the transition page and other pages with these formula inputs. Just one more thing I'd like to note on this transitions page. You can see here that the probability of going from the well state to the well state is just entered as capital C. And that's not a variable that we've defined. That's actually a keyword that our modeling package uses, which represents one minus the other transition probabilities. And so, for example, let's say we're looking at the natural history strategy. So for the natural history strategy, we have this probability of going from well to sick. We also have a probability of going from well to dead that applies to the natural history strategy. And then if you don't undergo either of those two transitions, the only other possibility is that you stay in the well state. And so what this capital C represents here is the complement of those two other probabilities. And so it will automatically calculate one minus the other two probabilities to get the probability of remaining within that state. And so that gives us a nice shorthand for avoiding a bunch of sort of one minus calculations in our transition page. So moving on to the values page. On the values page, there are two different sections. There's the health values page, you can see in this tab right here, and then there's the economic values page, which is the next tab. So on the health values page, we define the different line items that represent health outcomes in our model. So for example, here we're defining life years in the well state, life years in the sick state, and then qualities within each of those states. And I'm expanding these just because within each one of these line items, there may be different sort of ways in which those individual line items accrue. So just as an example, let's say we're looking at well qualities. So well qualities actually let's start with the well life years first. So well life years accrue for both strategies. So we've set the strategy here to all, but they only occur within the well state. And so for every cycle in the well state for both strategies, we're going to get this much worth of well life years. And the amount, of course, is the cycle length in years. So if you spend a cycle in a particular state, however long that cycle in years is how many life years you get for that state. And similarly, we define sick life years as occurring within the sick state. And so like this, we're just defining some state residency outcomes. For qualities, we're similarly defining this. Except in this case, qualities are based off of strategy because there are different utility values for each strategy in the well state. So we have an entry for natural history, which uses the utility value for natural history, and then we have an entry for the new drug, which uses the utility value for the new drug. So actually, before I go to that, we can go to economic values. And economic values work much the same way. We define a set of different values, and then for each one we define the different ways that those values accrue for different strategies and in different states. So for example, for medication costs here, because we're comparing against natural history, this cost only applies to the new drug. And so we have an entry here only for the new drug. And it only occurs during the well state because in this particular model, we're assuming that they get the drug only when they're in the well state. And then this formula here represents the cost per cycle of that drug. Next, we have a terminal care cost. And so in this case, we're actually modeling not a state residency cost, but a cost that occurs upon the transition between the sick and dead states. So under state here, instead of selecting one of the individual states, we're selecting the probability of going from sick to dead. And so this cost of a hospital stay, or cost of a hospice stay, will be applied every time someone transitions from sick to dead. And so that's the values page. Next is the summaries page. And on the summaries page, we're going to take those individual line items and aggregate them into aggregate quantities. And so under health summaries, we're defining life years and qualities as the sum of their constituent parts. So, for example, life years is the sum of well life years and sick life years. If there are other states, we can put in their components into this calculation. And in addition to that, because this is a health outcome, we're going to assign the willingness to pay to life years and to qualities. And so in this case, we're assigning a willingness to pay of $100,000 per life year and $150,000 per quality. And so that willingness to pay is automatically going to be used in the calculation of, for example, net monetary benefits. Next, we have the economic summaries. And so here we've defined healthcare system costs as the sum of medication costs and terminal care costs. And of course, if we wanted to, we could define additional cost summaries. For example, if we wanted to run something that was purely based on medication costs, we could do that. If we wanted to run the model using a societal perspective, we could add a summary which included some indirect costs. And so we can define any sort of different definitions of costs that we wanted to, and then use them in our cost effectiveness calculations. And so with that, we've gone through the main process of building a model, of the different pieces of a model. Just to add a couple things to that were not considered in the simple model. So in addition to the variables page, we also have a tables page where we can define tables of information that can be pasted in from Excel and then referenced, for example, using lookups. And so that functionality we're going to see in a subsequent model. There's also a code editor which allows you to define a series of R scripts to be run prior to running the model, which allows for defining custom functions or doing estimation tasks. And in some sense, it's the equivalent of the Visual Basic editor in our platform. It allows you to expand the functionality of these models beyond what we've anticipated. And so with that, we've completed the demo of building a simple Markov cohort model. Now, quickly, I'd like to talk about some more complicated cases, just how sort of the additional functionality that's available to handle them. So just one question that users have had in this process is why we use a long-form table rather than a matrix to specify transition probabilities. And so the reason that we've done that is there's a few reasons that make it more convenient to do it this way. So first off, oftentimes transition matrices are very sparse. There's a lot of transitions that are simply not possible. And because of that, we find the long-form approach to be more convenient because they allow you to just omit those entries. And so instead of having a gigantic transition matrix, often you have a very approachable, limited number of transitions that you need to define. Also, this allows for it to be much easier to define transition probabilities which depend on strategy, because for a given entry, we can say whether it's for strategy A, strategy B, or for both. And that makes it really nice and easy to define transition matrices for both strategies and make clear what's strategy dependent and what is not. Some additional aspects of building Markov cohort models, which heRo3 makes convenient. So one of them is handling time-dependent transition probabilities. We have a keyword that you can quite simply reference to develop to define time-dependent transition probabilities. In Excel, if you want to do that, you've got to manually create a transition matrix for every single cycle for which those transition probabilities differ. In heRo, it's just a matter of writing a formula such that it calculates that transition probability as a function of time, and it will automatically handle the process of creating those transition matrices for you. Similarly, in Excel, if you want to have transition probabilities depend on how long you've been in the state, you need to manually create a ton of tunnel states, whereas in heRo3, again, you just reference our special variable for state time, and those tunnel states will automatically be created for you, and you can control how many tunnels you want to create. Rescaling transition probabilities to reflect the cycle length is easy in heRo3. We have a function for doing that, as well as a whole host of functions for estimating transition probabilities as a function of survival distributions. And when we get to looking at partition survival model shortly, you'll see that we have a really wide range of functionality for dealing with survival distributions. And I just want to note at this time that all of that functionality that you're going to see for partition survival models is also totally applicable to Markov cohort models. You'll still be able to use all that functionality to estimate transition probabilities. And so, based on all these conveniences, we've gotten a lot of feedback from our testers that this substantially reduces model development times. It really allows them to build models in hours that would take them days, maybe weeks to build in Excel. And so, we really believe that we've achieved many of the goals that we've set out to achieve. So another efficiency in heRo3 is, of course, the output. Once you define the model, once you go through the process that we just described, building that Markov cohort model, you immediately have output displays available to you that show those different costs and outcomes, as well as cost effectiveness, the efficiency frontier. All of that is available to you immediately. Whereas, of course, in Excel, you need to set up those visualizations on your own, and that takes a decent amount of time to do. And if you want to export that output from the heRo3 platform, we have simple buttons for generating that, for exporting that, so that you can use it in Excel. We can also dump the entire results of a model, really everything from the inputs to the intermediate calculations, the results of intermediate calculations, to the final result outputs, to one large Excel workbook. So you can use that to essentially audit a model and pull out anything that you want to display from that. So with that, I'm going to do a quick demo of the output displays in heRo3. So going back to our simple Markov cohort model, in this left-hand sidebar, we've sort of seen the model editor, we've seen the variables page, tables, and code editor. I'm going to jump down to the reference or base case results page. And you can see I'm going to this page, and the first result I get is the trace. And so this diagram shows the probabilities of being in each of the 3 different states that we've defined over time. Currently, we're looking at it for the natural history strategy. So you'll note that below this sort of top-level tab here, we've got a set of options for different ways to display this data, different visualizations. So right now, we're looking at the line chart, but we can very easily change that to a stacked area chart if that's how we want to visualize it. And so now we can very easily see sort of how the time in the model divides across these 3 different states. Now, if we want to switch from natural history to new, we can do that. And if you look at how the sort of chart changes, you can see the difference in the trace between these 2 strategies. And so for natural history, they spend less time in the well state and less time, or more time in the dead state. So over here on the right-hand side, you can also see we have this section called user override values. User override values are input variables that we've pinned that we can change on the fly here and see their impact on the results. So, for example, let's say I want the impact of changing the probability of getting sick for the new strategy on this trace. So, for example, I'm going to take it down from 30% per cycle to 20% per cycle and just have it recalculate. And you'll see the amount of time spent in the sick state, rather the patient spent more time in the well state. And it was just as simple as that. So if we want to change this back to 30%, we just rerun the model, recalculate, and we see a nice transitional animation for that effect. Now, I just note quickly here that since you're looking at this over the WebEx, these transitional animations are going to look quite so smooth. But when you're doing this live, all of this is nice and smooth, and it's very easy to see what's changing in the results when you change an input. Now, I'll also note here that, of course, all of these outcomes that we're going to look at, all these output displays, have tabular views, and so this is the tabular view for the trace. You can see cycle by cycle exactly what the different probabilities are for each of these, being in each of these states. And we can control the precision if we like, change it to 3 digits. And so these are the probabilities of being in each state over time. Moving on to outcomes. So for outcomes, we can look at every single one of those health summaries that we've defined. So for example, here we're looking at a chart of life years for a natural history and the new strategy. You can see the breakdown of well life years, sick life years, and the total. If we want to, we can switch that to a waterfall chart just to see how those individual items add up to the total. If we want to look at qualities, we can do that over here. We can change it from discounted to undiscounted numbers. If instead of looking at the absolute numbers for these two strategies, we want to look at the differences, we can just select difference over here. So this is the difference of natural history versus new. If we want to flip that around, we just select new over here. And now we're looking at new versus natural history, so you can see that there's a gain in well qualities for new strategy. There's a smaller loss in the thick qualities for a net gain in the total qualities. And again, we've got our user override values here, so we want to see the effect of changing the probability of getting thick on this result. On the difference of qualities, we can do that. Next, we have the cost, and so this is similar to the outcomes page where we can look at the breakdown of costs for these strategies. Got a waterfall chart, a bar chart. We can, of course, do all the configuration over here that we saw in the previous one. We can go to a tabular view. So we have all these options for these charts. Next is net monetary benefit. And so what this is going to do is it's going to take one of our outcome summaries, one of our health summaries that we specify, in this case life years, and it's going to monetize that according to the threshold that we specified, the willingness to pay threshold that we specified for life years. And then it's going to subtract the increase in cost from those. And so you can see here that for comparing new versus natural history, there is a slight gain in net monetary benefit, meaning that it is cost-effective at the willingness to pay threshold that we specified for life years. And then finally, we have the CE frontier here. So you can see we've got our two strategies here, and they're both on the frontier. And then this line represents the ICER between those two. Now, this efficiency frontier, it's all very nice and animated, and we'll get into that once we've got a case where we have 3 or more strategies. So that will be a slightly more interesting case to demo that. Now, this is just our base case results. Moving beyond that, of course, we have results for various sensitivity analyses. So here we have value-based price calculator. So it's calculating right now because you changed the override value. But this line here represents the relationship between the willingness to pay threshold that we use and the price that we can charge for the drug. So in this model, we have a parameter called cost new, which is the cost of the new drug per cycle. And that's what we're using in this VBP analysis. So on this axis, it will represent the cost of the new drug per cycle that's necessary to be cost effective at the specified willingness to pay threshold. And so very quickly, after we've defined our model, we just fill out these items on the right-hand side, and we have a VBP calculator. It's that simple. And if we want to look at this to a larger willingness to pay up to 100,000, we just change this over here, and now we can see the results for the willingness to pay up to 100,000. And this VBP calculator, I would note that it works even in the presence of multiple comparison strategies. And so if we are comparing versus, let's say, 2 or more other strategies, we'll see the value-based price versus each individual comparison, plus we'll see the lowest of those value-based prices, which is the price that will make your drug preferable to all competitors. Now, in addition to VBP, we have, of course, deterministic sensitivity analyses. And so we're going to run that. And so for each one of these outcomes, you can see we've got a tornado plot showing the impact of various variables on the results. And so right now we're looking at life years, and you can see these are the 3 variables that we've set to vary that impact life years. The other variables that we're varying that don't impact life years are omitted because they wouldn't be very interesting to show on this chart. Now, if we go to something like net monetary benefit, you'll see there's a larger set of factors that are impacting the NMB. So we've got base case results done, we've got value-based pricing, we've got deterministic sensitivity analyses, and right now we're in the process of developing our probabilistic sensitivity analysis module. And so really the goal here is that really immediately after you've set up your model, you're going to have all of this available to run, all these results available to you. Now for VBP, it's just a matter of defining essentially what strategy you're running it for and what your price parameter is that you're sort of working with. For DSA, it's just a matter of sort of checking off which parameters you want to vary and what range you want to vary them over. So just to show you what that looks like, this is our DSA inputs page, and you can see we've selected to vary these parameters. And for each one of those parameters, we got a low value and a high value. And we can define those in different ways. So for example, for this parameter, we just specified the range over which we want to vary it. For this parameter, we're saying we want to do plus or minus 0.2 from the base case value. And then for these two, we're doing, sort of plus or minus 25% of the base case value. And because we've got this sort of keyword here, BC, which references the base case value, it's very easy to define these low and high values as a function of the base case value. And so really, once you build your model, you very quickly get to your result. In Excel, you got to build your output modules. In this thing, you very quickly define them and you're up and running.
Check some more so you can show it.
Okay.
Can you check some more so you can show display
The sorting?
Oh,
just as an example, if we want to add an additional variable here to this DSA, let's say we want to also vary the cost of a hospice stay. So right now it's $85,000, but let's say we want to vary that from half that to twice that. And so we would do, in the low value, we'd do BC, which is the base case value of $85,000, times 0.5. And so that's going to yield a value of half the current base case value. And then on the high side, I'm going to do BC times 2. And so that's going to vary it to, between half 85,000 and twice 85,000. And so now when I go back to the DSA page, this DSA is going to rerun. And because the terminal care cost impacts the net monetary benefit, what you're going to see is that scenario gets added into this tornado plot, and it happens to be the least impactful of these scenarios, so it gets shown at the bottom. Very nice and easy to create and modify your DSA. So that covers our output displays as they currently stand. Next, I want to get into partition survival modeling. So we went through our simple example of a Markov cohort model, but now I want to go through a similar set of examples for doing partition survival models. So just briefly, the difference between Markov cohort models and partition survival models in this platform is really mainly about the transitions page. And so on the transitions page for Markov cohort model, of course, you're defining your transition matrix. For a partition survival model, you're defining the distributions of PFS and OS for each strategy. Now, our current approach to partition survival models is limited to 3 steps. So, for example, pre-progression, post-progression, and dead, which patients are assumed to go through in that order. However, we're currently building a more advanced partition survival module, which allows you to define any number of states and define the sort of trace calculations for those states directly. And so this would allow for more advanced partition survival models. For example, if you want to break patients up into responders and non-responders, and then model them using separate partition survival models. For example, you could do a 2-state model with, relapse and dead for the non-responders, and a 3-state model with response, relapse, and dead for the responders. That more advanced functionality will allow you to do that. It will also allow you to do things like model, test, and treat strategies, where you'll be able to separate out the patients who test positive for a specific marker versus those who test negative for a specific marker, and allow different pathways for those two groups. But currently today we're demoing this sort of more simple partition survival functionality, which is built around this standard 3-state model. Now, one thing I'd like to additionally call out for partition survival models is that on that variables page that we looked at, there's a second tab to it specifically for defining survival distributions. Now, that tab is also there for Markov cohort models, but of course, survival distributions are so fundamental to partition survival distributions that we really want to call that out at this point. And we'll see an example of using that page in this model we're going to do. And really what the purpose of that tab in the variables page is, you can define a set of survival distributions and define some survival distributions as a function of other survival distributions, for example, using proportional hazards approaches. It makes it really nice and easy to build up relatively complicated survival modeling methods using this system that would take a lot more time to build in Excel. So just to sort of go over the models we're going to build. So we're going to build 3 different partition survival models. It's really the same model, but we're going to sort of add additional complexity with each step. And really where we're going to start is with a simple model based on a TPP, based off of really the follow-up of data that's currently available. We're then going to transition to a model which projects beyond the follow-up using a parametric curve. And then finally, we're going to look at what we can do when we add an additional strategy that requires a very different modeling approach for PFS and OS. So, use case number 1. Let's say we've got a target product profile for a new product, which we'll call sunitinib, which is a TKI for renal cell carcinoma. And that this TPP sets forth assumed gains in median PFS or OS versus, in this case, best supportive care. And that you have some Kaplan-Meier data for best supportive care that's currently out there based on, for example, registry data or some other source. So this is a pretty typical example. And so what we would do as an analyst, of course, is to take that PFS and OS data for BSC. We would digitize that, and we would get survival probabilities for that Kaplan-Meier data. And let's just say that that data goes out to 5 years. And now, based on our TPP, we'll assume that the gain, the estimates are, rather based off this data, that the median PFS for BSC is 13.4 months for PFS and 32.2 months for OS. Then we'll take into account our TPP, which states that with sunitinib, the median PFS increases to 20 months, which represents a hazard ratio of about 0.67 just based on the ratio of the medians, and the median OS of 41.9 months, which is a hazard ratio of about 0.72. So we're going to start with that and model it based off of those parameters. So what I'm going to do is I'm going to go back to heRo. Going to go back to, this is what we call the modeler workspace. This is where you see all the different models that you have defined as well as a set of templates that you can work with. And I'm just going to open our simple example model here for this first use case. And so what I'm going to do is I'm going to go through this fairly quickly. So just on the settings page, you can see we're doing a model. It's a weekly model, weekly cycle length up to 5 years. We've got no group, so it's a homogeneous model. Prediction survival model, a simple one, so of course it's just the standard 3 states, progression-free, post-progression, and dead. Now just note here that while we can't add additional states with this simple partition survival module, we can change their name. So if you wanted to do, for example, relapse-free, post-relapse, and dead, you can do that. Next we've got our strategies, so of course best supportive care and sunitinib. And then on the transitions page, here you can see instead of defining our transition matrix, we're defining for sort of PFS for sunitinib and BSC. We've got our formula which represents that survival distribution, and then for OS we also have formulas which represent the survival distributions. But of course the real sort of meat of this model is what's behind this formula. How do we define these distributions? And so I'm going to get into that pretty briefly. So first we're going to go to the tables page, and this is where our digitized data comes in. And so for best supportive care, we've got our table of survival data. So here we have a table of survival probabilities at various times for BSC, and so this is in months. So for example, at month about 7.5, there's a probability of survival of 0.74, 74% for PFS. And similarly for OS, we've got our table of data here showing the OS probabilities that we've digitized prior to building this model. And so what we're going to do is we're going to take those tables, and in the variables page, we go to the survival distributions tab, and this is where we're going to start defining our survival distributions. And so first thing we're going to define is a survival distribution we're calling BSC PFS KN. So this is the PFS Kaplan-Meier for BSC. And we're using a function, a helper function called define serve table. And define serve table takes as an argument this table that we've defined. And it's going to turn that into a survival distribution essentially by looking up the appropriate survival probabilities at the appropriate time. And so like that, we have our Kaplan-Meier for BSE PFS. And similarly, for OS, we use defined survive table, defined surv table, and we pass in the table of OS survival probabilities. And like that, we have our table, our survival distribution for OS. So that handles survival for BSE and for PFS and OS for BSE at this point, because at this point we're just using the Kaplan-Meiers. And we're just going up to the duration of follow-up for the Kaplan-Meiers, which is 5 years. Next, we need to handle PFS and OS for sunitinib. And the way we're going to do that is using those hazard ratios that we derived from our TPP. And so in our formula here, we're going to use the apply hazard ratio function, apply HR. And the way that works is we pass in as the first argument the survival distribution to which we're applying the hazard ratio, and as the second argument, the hazard ratio which we're applying, which is just a parameter that we've defined on the parameter section of the variables page. And so like that, we're defining an alternate version that BSE, PFS, Kaplan-Meier with this hazard ratio applied, the PFS hazard ratio for sunitinib versus BSE. And similarly for OS, we take the OS Kaplan-Meier for BSE and we apply the OS hazard ratio for sunitinib versus BSE. And like that, we've got our survival modeling. And these survival distributions that we've defined here, for example, FUN OS KM, that's exactly what we're referencing right here. And so like that, we've defined distributions of PFS and OS for sunitinib and BSE using Kaplan-Meier data for BSE and using a proportional hazards approach for sunitinib. And just skipping ahead to the results here, you can see is our trace, and you can see it looks like Kaplan-Meiers. We've got these Kaplan-Meiers for PFS and for OS, and if we switch from BSE to sunitinib, you'll see PFS and OS is a bit higher, reflecting the hazard ratio that was applied. So this is a simple case, but what we can do is make this a little bit more complicated, and that gets us to use case number 2. So now, instead of just working based off of the observed data, we want to project beyond that observed data using up to 10 years. And so what we're going to do to accomplish that is we're going to use parametric functions to project from year 5 to year 10, so picking up where the Kaplan-Meier left off. And we're going to do that using a Weibull distribution, but we're also going to set up the model so that we can switch it to a log normal distribution so that we can examine that. And so with that, let's take a look at the second iteration of this model. I'm just going to open up the version 2 of this model, skipping ahead. Though note this would only take about 10 minutes to set up, 5 to 10 minutes really. And so what we're going to do here is on the variables page, we didn't see it before, but we have, or actually we haven't gotten to it before, but we have parameters for PFS and OS for our parametric distributions that we've estimated. So we've got our shape and scale parameters for the Weibull distribution for PFS. We've got shape and scale parameters for the Weibull distribution for OS. And then since we also want to run log normal, we've got parameters for the log normal distribution here as well. And so these are the parameters of the parametric distributions we're going to use to project from year 5 to year 10. Now, in addition to that, we're setting up a couple additional parameters here, and these are, we like to call them indicator variables. And these are just going to be what we use to switch between using the Weibull distribution and the log normal distribution. So this variable, for example, OS dist. We're putting in this value here, just in quotes, Weibull. And so when this is set to Weibull, we're going to make it so that it uses the Weibull distribution. And when it's going to set, when it's set to log normal, it's going to use the log normal distribution. Elsewhere, we're going to have a conditional function which essentially reads this variable, and we'll use the appropriate survival distribution depending on whatever it's set to. And so based on that, we're going to be able to switch between those two distributions. Now, switching to the survival distribution stage, you can see that we've got a lot more survival distributions defined here. So let's start with PFS for BSE. So we have our BSE PFS Kaplan-Meier, that's what we had before. But then next we have another variable here, BSE PFS Weibull. And that's defined using this formula, defined survival, which we use to define a parametric survival distribution following a given parametric form and a given set of parameters. So you can see here the first argument we're passing in dist equals Weibull, meaning that it's a Weibull distribution. And then we assign the shape and scale parameters to the parameters that we define for PFS shape and PFS scale. And so this PFS BSD Weibull represents a Weibull distribution that we can use. Similarly, BSD PFS log normal represents a log normal distribution, and here we're telling it to use log normal, and we're passing in the appropriate parameters for the PFS log normal distribution. Now, finally, we have this variable BSD PFS, and this will represent the combination of our Kaplan-Meier and whichever parametric distribution that we use to extrapolate beyond that point at 5 years. And so what we're doing here is we're using the join function to join together two survival distributions. And the first survival distribution that we're going to join is the Kaplan-Meier. So we're going to start by using the Kaplan-Meier, and we're going to use it to 60 months, 5 years. And then the thing that we're going to join it to is either going to be the Weibull distribution or the log normal distribution. And we're using an if statement here so that if the PFS distribution is a Weibull, we use the Weibull, and otherwise we use the log normal. And so this join function will result in a distribution which reflects the Kaplan-Meier for the first 60 months, or the first 5 years, followed by whichever one of our parametric projections that we're going to use beyond that point. And similarly, for OS, we sort of define our two parametric distributions, and then we join whichever one we're using with the Kaplan-Meier. That's the exact same process. And finally, for Finitinib, all we're doing is we're taking the final PFS distributions and applying that same hazard ratio to it. So take the final PFS distribution, and we apply the PFS hazard ratio, and we take the final OS distribution, and we apply the OS hazard ratio. So we're stringing together these various functions for defining and modifying survival distributions to get the exact modeling approach that we want to accomplish here. And so once we look at the results, you'll see now we're going out to, oops, I had a slight problem in this setup. Apologies, looks like I accidentally deleted something. So this is a good opportunity to use the undo feature here. So I accidentally just deleted this OS distribution variable as I was looking at this, and so I just used the undo function to fix that. And so you can see that it calculates properly, and we're using the Kaplan-Meiers up to 5 years. And at that point, our parametric projections take over. I'm just going to take this to a stacked area chart so that you can see this more clearly. Our parametric projections pick up exactly where the Kaplan-Meier leaves off. And over here on our override values, you can see that I've got our override values set for OS distribution and PFS distribution. So right now, this is set to use the log normal. But if I set the OS distribution to use Weibull instead here, just by typing in Weibull, you'll see that this OS distribution is going to change right here. It's a little bit lower. So that represents using a Weibull for OS. You change it over here to PFS. So we calculate, and you'll see the PFS distribution changes. And so like that, we can very easily set up multiple alternate projection methods and switch between them. So there's one more step that we're going to go through just to show off how to use this platform in a sort of realistic case. So our use case number 3 is now we have a new drug entering the market. Now, previously we've been comparing against best supportive care, but of course we can just as easily compare against a competitor drug, and that's what we're going to do here. So we're introducing nivolumab, a new entrant into the market, which is a immune checkpoint inhibitor. And many people believe nivolumab can produce durable cures for some subset of the patients, both for PFS and for OS. And so we need to add this new market entrant into our model. And because of the mechanism of action, because we believe, or some people believe at least, that this new entrant is going to produce durable gains for PFS and for OS, we're going to model it using a Weibull mixture cure model. So we're going to do something a little bit more advanced that's outside of the sort of existing setup for the way comparators are being modeled. And so in Excel, this would involve, wrangling a new set of calculations to handle this, and you'd have to spend some time structurally modifying the model so that it actually allows for using Weibull mixture models. But we're going to do this in a few minutes in heRo3, and I'm actually going to walk you through that process live rather than opening up a new model. So first thing we're going to do is we're going to create a new strategy. Of course, you need a new strategy to represent nivolumab, and so that's what I'm going to do. So I'm just going to do new strategy, I'll call it new, and this is going to be nivolumab. And so next we're going to just go to the values page and define a few things for nivolumab. So first thing is we're going to need to make sure that it has a medication cost associated with it. So I'm going to the values page under medication costs, and I'm making sure it gets the medication costs. Strategy to new. I'm going to set the state to progression-free because they get the cost of this during the progression-free state. And for the moment, I'm just going to hard code the cost per cycle of nivolumab to, let's say, 5,000. So that handles making sure that we're costing out the medication of nivolumab. Next, we need to go to the variables page and start defining a few parameters. Though we're actually just going to skip over that in the interest of time. We're just going to directly sort of hard code those parameters, but we can very easily sort of set those parameters up over here. So I'm going to go to the survival distributions page, and I'm going to create a new survival distribution called PFS fun. And for PFS fun, I'm going to define a formula which represents the PFS distribution for sunitinib. Sorry, this is not fun. This is PFS new. This is our PFS distribution for nivolumab. And what we're going to do is we're just going to set the formula to define survival cure. So this function defines survival cure. It's a lot like define survival, except this is specific to cure models. And so it takes a similar set of arguments. So first we're going to define the parametric form for this cure model. So we're going to use Weibull. Then we're going to pass in the first parameter, theta, which is the cure fraction. So we're going to get the cure fraction, this is for our PFS, so we're going to set the proportion of patients who never progress or die to 30%. Make that 35%. And set the shape and tail parameters. Shape equals 1.2 and 1.3. Scale equals, let's say, 30. And so that's our mixture cure model for PFS. Next, we're going to do the same thing for OS. So we're going to do OS new. And we're going to do define survival cure. We're going to do a Weibull distribution. Set the cure fraction to OS a little bit higher, to equals 0.4, so 40%. Equals 1.2, scale equals, let's say, 50. So we've defined our PFS and OS distributions. Now we just need to go to the transitions page and reference them appropriately. So for PFS, we're going to put PFS. And then under OS, we're going to do OS new. We're just referencing the survival distributions that we just created. And now we should be ready to go. So it's going to recalculate the model, but now we have the new strategy here. And you can see the new strategy here uses our Weibull mixture cure models for PFS and for OS. Now, if we wanted to, we could spend a little bit of extra time and define some Kaplan-Meier data for this and join these cure functions to it. But the point here is that very quickly we can define a totally different modeling approach to another strategy. And even if it's using something relatively advanced like a mixture cure model, it really takes no time at all to put together. And we're ready to look at the various costs and outcomes for our model. So those cover our three use cases for partition survival models that we wanted to cover. We didn't cover all the partition survival model functionality, but that should give you a pretty good taste of what the process is like, particularly for building an early model. Now we're going to move on to covering a few general points, and then shortly after that we will get to questions. So I'd like to quickly discuss first-time use. So when you first open up heRo3, once you've been given access, actually even before that, Currently during the beta testing, we do ask that you use the Google Chrome browser. Other browsers are not currently supported, though support will be added in the future. And at the moment during the beta testing, your model data, your user information is being saved locally. So all of your models and all of the sort of tabular data that you put into these models is not stored on our server, it's not retained on our server. It's stored within a special area of the browser, which is only accessible when you're currently on the heRo3 application. Now, that's going to change as we move into the full release of the platform, but right now, we're not actually storing your model data. So because of that, because of the way this is currently set up during the pilot testing, that means that you will, when you save a model on our platform, it's only accessible from that same device. Now, that will, of course, change once we go to the full launch, and then you'll be able to access your models using your user account from any device. Actually, this first-time use screen, I should make a note here. We've recently pushed an update which involves creating user accounts. So previously, access of the platform was available to anyone with URL. As of the end of last week, you now will need to register for an account. And so we don't have a screenshot of that screen right here, but I can very quickly show you what that looks like. So heRo3.herops.io. So when you go to the main URL here, you'll see that there's a login screen, and if you don't have your account yet, you just go to register, and you follow the process for registering, and you'll get an email to confirm your account, and then you'll be able to log in. But once you've logged in, you'll get this screen, and this is essentially our end-user license agreement. So you need to accept that. But also there's a little icon over here which allows us to store data within the browser area, and so you'll need to hit allow. Otherwise, you won't be able to load and save models properly, so please hit allow. And so in order to, once you've done that, you'll get to this modeler workspace screen. And so in the modeler screen we saw it previously, quickly, but there's a few different panels here. Up top here, there's buttons for creating new models. There's a button for new Markov cohort model, a button for new partition survival model. There's also an area here for showing you the models that you've created previously, and you just click on any one of those models if you want to open them. And then below that, there's a section for model templates, which allows you to open up a model template, and each of these templates exemplifies certain functionality in the platform, both to demonstrate that functionality as well as to potentially give you a starting point to work with when building a model. So for example, here there's a template for doing time to discontinuation, which reflects using a partition survival model where we assume that patients are not necessarily on treatment strictly during PFS. They may discontinue before or after they progress. And so each of these templates demonstrates some kind of useful functionality. So the next thing that we want to bring up is backing up models. The Chrome cache, which we use to store models, is not really used, it's not really meant for permanent storage. And so what we recommend is that you not rely on it for storing your model. So if you have an important model that you want to save, rather than simply hitting the save button, you should also export it to a file. And that export functionality will essentially download a file format which represents the data contained within your model, which can then be re-uploaded to the platform to open it up. And this will make sure that you never lose your data if something happens with your Chrome cache. And it will also ensure that as we migrate to the final release of the model, where those models are going to be stored on a server, behind a firewall and behind your user account, that you'll be able to upload that information to the platform. And there are instructions for doing that, but I'll just quickly show it. So let's say we want to work with this model here that we've defined, so we'll open it up. So what we can do is we can go to this export section on the left-hand sidebar here, this up-down arrow section. And what we want to do is go to export to JSON. JSON is just the file format that we use. And when we hit that, it'll just automatically download the model to to wherever your browser downloads things by default. Usually it's a download folder. So if I hit that, you'll see it downloads the model. And then if we want to import it, we would just go back to the model workspace, we'd hit import model, and then we'd browse to wherever we downloaded that model to, and it would open it up just as easy as we clicked on it over here.
Well, here, can you still show export to Excel, not transparency?
Yeah, so another thing I just want to quickly show is export to Excel. So I'm just going to open our simple Markov model here. Actually, let me go to a more advanced one just to demonstrate this. This is a Markov model that has state and model time dependency, so there's going to be a lot to look at. I'm going to go to the export functionality. So there's actually two other ways that we can export this. One, we can export this to R, and what this is going to do is it's going to download an RStudio project folder that allows us to run the model locally in R, that is, run the model on your local machine using your installation of R. And potentially that allows you to run the model using line-by-line debugging. And so if there's some error that's going on with the model, you'll be able to see exactly which line that occurs at. Or if there's some point at which, in the evaluation of the model where you want to peek under the hood and see what's happening, you'll be able to do that. Or if you just want to be able to run it without an internet connection, you can do that. And that'll just dump the results within R. You can also export to Excel, and what this is going to do is it's going to run the model and then generate an Excel workbook with all the inputs, all the results of the intermediate calculations, and all the final results. And so I'm going to do this now, and it's going to take a moment as it calculates the model, and then it's going to download that Excel workbook. And so I'll open it up in Excel, and you'll see there's a bunch of different tabs here. So for example, this is the setting tab. You can see there's the discount rates for cost and advocacy, there's the cycle length, and this is defined in terms of days, the number of cycles. We're just going to jump ahead here to some intermediate results of calculations to the transitions. And so this table here shows every single transition matrix that was calculated going into this model. So you can see we've got a natural history strategy here. This is the transition matrix for the first cycle that is used. And you can see the use of the from states. And just as an example here, this is a model that we defined with 3 states, well, sick, and dead. But because we referenced state time in the calculations of the sick state, it automatically expanded it into a set of tunnel states. And so those tunnel states are included in these transition matrices. And so you can just sort of scroll through this and see for any particular transition in any particular cycle exactly what probability was used. And similarly, we can do this for the calculations of the values over time. So this is going to show, for example, the number of sick qualities that get sort of accumulated in each state over time. And so this is, you can really peek under the hood and see exactly what's going on by doing this. It's a complete dump of everything that R calculates. So moving on. So we actually just covered that, the different ways of exporting information from the platform. Undo and redo, we already have an example of this where I accidentally deleted something. And so just to reiterate, up at the top here, this is the undo arrow, and this is the redo arrow. And you can go back as far as 10 actions. It will remember the last 10 actions you did. So if you made a mistake a couple different actions ago, you can easily go back to that. And if you decide you want to undo undoing those actions, you just hit the redo button a few times, and you can just step backwards and forwards in time using that functionality. Now, the last thing I want to mention here is help and support. We've got a lot of testers, and we're providing support to everyone during this testing phase. And so if you have any questions, the first place to look is our heRo3 guide and FAQs. And so the way you can get to that is when you're within the platform, you just hit this help button here, and it will take you to the guide. And there are various different pages that you can see for different aspects of help. So for example, here's a help page for the strategy page. And you can see it provides a screenshot as well as some instructions as to what to do on that page. And so we've got a variety of different articles on this page. So if you've got a question, there's a good chance that the answer to that question is in that guide. And so that's the first place to look. Now, if you don't find an answer there, you can always contact those on Slack. and we can send invites to Slack. And Slack, just for those who don't know, is a work-oriented chat application that we have many of the beta testers on. And so you can ask us questions over Slack. Of course, you can send an email to our support email address, which is heRo3support@pai2.com. So reach out to us if you have any questions or need any help that isn't already taken care of by the guide. And so at this point, I'd like to thank everyone for their interest in heRo3 and open up the floor to the questions I'm sure you have after this sort of long walkthrough. So anyone who would like to ask the questions, please do so now. Please remember to unmute yourself if you muted yourself previously. So the floor is open.
Yeah, hi there. James Ryan from AstraZeneca global team. What validation work have you done with payers around the world to make sure that they would accept this?
So, Jared, do you want to talk about that?
Yeah, I mean, that is an ongoing process. ICER has been involved in the pilot testing of heRo3 from the very beginning, and we've been in extended discussions with them. I anticipate that in all likelihood they are going to be deploying the platform in their own organization for the economic evaluations that they undertake. One of the companies that was involved in the development initiative, namely Merck, very much has as a long-run strategic objective would like to be doing submissions in R rather than Excel, and heRo3 was, or is rather, part of that long-run sort of tactical plan that they have for getting payers and HTA authorities to accept submissions in R. The problem with R is that not a lot of people are R programmers, and what heRo3 does is it brings these very robust, powerful open source modeling packages to the world of modelers and analysts who can be conversant or become conversant with sort of R syntax, but who are not R programmers. So this is very much a work in progress right now. I think that the sweet spot for heRo3 at the moment is unquestionably early models. I mean, what Jordan was doing live, especially in the area of partition survival models and oncology, I can't even guesstimate the number of days it would take a programmer in Excel to replicate what he's just done in the last hour. So, you know, the ability to develop early models, to have those models be flexible and not always have to drop a dime with your HEOR consultant and get a bill for substantially more than a dime for the modifications to an Excel model, that's where I think the great power is going to be here. Also, model validation. In reality, you know, our experience at least is that most companies do not validate the models that they're building in Excel. Why? Because it takes, it's not insubstantial in terms of the cost, and validation, it's impossible to QA a model by looking in Excel by looking at all the cells. So in effect, the only way, practically speaking, to validate it is by building a second model, you know, perhaps without the user interface that is designed to generate hopefully the same answers. Of course, if it doesn't, then you're left scratching your head as to which one was wrong and which one was right. That's sort of the haphazard approach to model validation. This opens up a tremendous opportunity to validate work that's being done in Excel. And as Jordan mentioned, we know that you know that what the answers are that heRo3 is spitting out. There are no errors in the programming code.
Yeah, no, it's interesting comments. I will disagree with the extent to which you talk about the downsides of Excel, because I don't think all of them necessarily hold. I suppose the key question then is, you've talked about ISA in the US. What's your intent for NICE, SMC, PBAC, PCODA, TLV, and other international payers?
In fact, through Google Analytics, we've been able, so we've reached out to HTA authorities in Canada and the UK. They've been a little bit standoffish, but we do know that they've been visiting the platform and using it. So I think that, we have not announced the price, and as ultimately a commercial offering, that may be part of the reason for the standoffish stance. I will tell you that we have promised to make this platform available without charge to academics, to students, and to HTA agencies and bodies. We do not intend to charge them for the use of the platform. So my guess is that their interest in it may increase a little bit once it's in an official commercial release and it's available.
Sure. Brilliant. Thank you ever so much.
Hi, this is Anju from Altramis. Along the same lines from the previous question, one of the reasons we've all historically built models in Excel is because of that whole transportability, right? So someone asks, you can easily send that model, to any SMC or any HTA body. How would this work with the heRo3? If we have to send the model to some payer or someone else, how do you do that? Do they need access to heRo3, or what's maybe you covered in the beginning? I dialed in a little late, so apologies for that.
I mean, there's a couple ways that might happen. So one is you could send them the model through the platform. You could give them a version of the model, and that would require that they have access to the platform. Though, as Jerry mentioned previously,
everyone will. Yeah.
We don't intend to charge, and so there's no reason they can't get that access. And so at that point, sending the model to them will be really as simple as it is to send them a model in Excel. But even if they decide that they don't want to run the model within the platform, it's always possible to export this model to run directly in R. If they want to run it directly on their own machine in R, they can do that. And R is, of course, freely available to install and is widely used in academic circles, including within the various ERGs, and so they should have no problem. I mean, if they want to run the model on their own machine using line-by-line debugging to see exactly what's going on, they'll be able to do that at their leisure.
And there have, in fact, been nice submissions in R. So.
Okay. Thank you.
Any other questions? Please feel free to speak up.
I have a couple of more questions, but I want to give opportunity to others first rather than asking all the questions.
I don't think there's any need to be shy. You go ahead with the questions and give them some more time to think about what questions they want to ask.
Okay, I'll I guess fill up the time. So, quick thing, with Excel, a lot of times some of these complicated models take a long time to run, for example, when you're doing these PSAs and all that. So what has been your experience with this kind of interface and runtime?
So our experience so far, I mean, we have not sort of finished the development of PSAs, so we're still, the jury's still out on that one, but we believe that there's going to be some modest performance improvements across the board on these models, but of course, really the performance is a function of how you set the model up, and there are going to be wide variations, and there are usually much more efficient ways to set up a given problem, but we don't anticipate models are going to take very long to run. We've done some fairly complicated models with lots of tunnel states, very complicated Markov models, and they run in a reasonable amount of time. but I think really the most critical time is not really the time it takes to run the model, I think, but the time it takes to build the model, and that's, I think, where we see the largest time savings.
Yeah. Okay.
But one thing I would note is that we have the advantage for something like the PSA for handling these calculations on the server and therefore potentially taking advantage very heavily of parallel processing. So we do have good reason to believe that when it comes to sort of the full scale of the PSA, we're going to be able to sort of get some pretty significant advantages there in terms of runtime. But that applies less so to just sort of running the base case of a model where you're just running it once and no parallelization is really practical.
Okay, thanks.
One more thing, Jordan alluded to it earlier. So this is going to be available as an enterprise level deployment either behind a firewall or running in the cloud. So that is to say, it can either be run on your servers behind your firewall, and therefore you control security and who has access to it. Alternatively, we are going to have available an enterprise deployment in an established sort of top-of-the-line cloud-based provider. We're not going to host it here at PAI. It'll be something like Amazon Web Services, Microsoft, IBM Cloud, something like that. So it'll have sort of the highest levels of security as we understand that models and data that people load in, that information is valuable, and if folks are going to be using a cloud-based application, they're going to want to make certain that that information is adequately protected. Jordan, you want to talk just for a second about the administrative wrapper in terms of how that's going to work with organizations and groups and individuals, and that for somebody with enterprise deployment, they're going to have control over who gets what?
Sure. So within sort of our cloud deployment, essentially we're going to group users into different organizations. So your company, for example, would be an organization, and within that organization, we would, once we set it up, we would define an administrator who would have the ability to define, to add or remove users and to define different groups of users, which helps sort of control access of information within your organization. And essentially, it'll be your own sort of little kingdom within the application that you'll be able to self-administer. And of course, we will put in place various layers of security to make sure that information is only accessed by those who are authenticated and authorized to gain access to that information. And beyond sort of our cloud-based multi-tenant offering where multiple companies are on the same set of servers, it will be possible to do a single tenant deployment where only your company is within those servers to sort of add an additional sort of layer of security to make absolute certain that there's no commingling of any data. And then as we move into sort of the release, we're going to start preparing for enterprise deployments behind firewalls, and that's something that we'll be willing to start discussing once the release takes place. And then at that point, once we're ready to do those deployments, you'll be able to have the application running actually behind your corporate firewall, not in the cloud. That way, you can further put it behind your own sort of IT protections. Any other questions before we close up? So this is the last chance.
So this is Anju again. Really, I have to commend you all on putting all your efforts to put this user-friendly interface and making it such a nice tool for us to quickly build models. primarily more on cost-effectiveness models, but are there discussions and interest in kind of doing these, you know, especially for the U.S., this cost calculators or budget impact models as well, or?
Absolutely. So we see this as a platform with limitless potential, and so we're looking in a lot of different directions for expanding the functionality, and one of those is, of course, building budgetary impact models. I mean, when you build a cost-effectiveness model, you're already building much of the guts of a BIM, and at that point, it's a matter of adding in sort of the, you know, defining the eligible population and sort of the inflow into the model, and then adding a few additional results displays and, you know, possibly removing information on outcomes. And so we certainly see that as one natural sort of passive expansion to this platform, and it's one we'd be very happy to talk about in the future.
And I would note that the only thing that stands between that path of expansion or the aspiration and the realization are resources. So as I think the owner of the LA Rams once said about George Allen, I gave him an unlimited budget and he managed to exceed it. Well, that's sort of the development initiative on heRo3. I mean, we literally have vastly exceeded the very generous development funding that we got from Merck, Novartis, and Amgen, and we are at the point where to do anything further in terms of refinement and further development of the platform, we need to make certain that there is a demand for it in the marketplace. We've got a development team of some very talented people in-house here who have been working on it, and unfortunately they like to eat. So that's really, I think everything will be dependent upon, you know, what we see in the months ahead, and in particular, you know, the official launch will be around ISPOR. And if we see there's uptake at that point in time, then I think it'll be pedal to the metal and we'll continue to build it out. If not, then I think we're going to have to take a careful look and ask ourselves whether or not the world wants a better mousetrap.
Thank you. Yeah. And how long is the testing phase going to be for any interested users at this point?
It probably about another 3 to 4 weeks.
Okay.
And what, as Jordan has alluded, there will be a period of time during which the app will be available both as a cloud-based, in terms of the cloud-based storage, and the pilot testing portals, URLs will still be available to allow people to be able to get the models that they've built and saved on their local devices to get them exported and then imported to the cloud-based application. So we're not going to be shutting anything down immediately. I would guess it would probably be about 6 weeks that the pilot test sites will be available. Most of you, I believe, have been directed to the heRo3.heroapps.io, which is the official and the latest release. So I don't think you need worry about that.
Okay. I have 2 technical questions. I don't know if I should ask them now or directly send an email to the address that you have on the screen.
You can ask them. If they're too embarrassing, we may just hang up.
Well, no, it's just more, you know, a lot of times in our models we do put in like the discontinuation rates and AE rates. So is that something, is it in the value section do we add, or where do we put that in to account for different discontinuation rate across various treatments or strategies and adverse event rates?
Well, in some sense, that depends on how you want to model it. For example, in a Markov model, perhaps you would define a state for on-treatment and off-treatment, and then discontinuation rates represent transition probabilities between those states. In sort of the example partition survival model that we looked at, if you wanted to model discontinuation separately from those states, what you could do is, yes, define a value which represents the probability of being on treatment, and then in the medication cost value, multiply that, you know, on treatment value by the sort of cost per cycle.
Okay.
There's certainly different ways to accomplish something like that, and it would depend on the circumstance and how you want to approach it.
Okay. And is there an adjustment for half cycle in those Markov models? I don't see it being called out. Maybe, I'm sure there is a way to do it.
So that's on the settings page, and we have different options. So we have an option, so treating it as if the transitions happen at the beginning of a cycle or as if they happen at the end of the cycle,
okay.
or you know, using the method where we average the sort of the two cycles. And so those options are available to select.
Okay, great. Thank you.
Let me just thank everybody for joining us today. We have provided a lot of technical support to folks who are new to the platform, and we get emails all the time. I would note that if you decide that you want to try building a model in heRo3 and the model simply won't run, you can't figure out how to debug it, Jordan showed it earlier, the export to JSON functionality with those little up-down arrows in the left-hand side, at the bottom of the left-hand toolbar, just export it to JSON and email it to the address that Jordan provided, and we usually are able to get on it pretty quickly, and most of the problems are not bugs with the platform, but just as a result of mistakes that people make in setting models up because the paradigm is new. So we're more than happy to help, and find that people get up to speed fairly quickly because of the structure and formalism of heRo3. So we're more than happy to help out here.
All right, I think that concludes the call. Thank you, everyone, for participating. Let us know if you have any comments or questions. Thank you.
Thank you all again.